We went pretty far so far. How far can we go? We can go really far, like all the way with this Fibonacci staircase analysis. But first we need some tools. We need some new ideas. Remember, like they said in the Matrix, ideas, lots of ideas. That's what we need. Let's say we have 4 balls and we want to put them into 3 boxes. Okay, so N is 4, the number of balls, and K is 3, the number of boxes. And the question is, how many ways can we do this? For example, here's one way. We can put 2 balls in here and 2 balls in here and none in there. Yeah, we can do stuff like that. How many ways can we do that? Well, here's a way to think of it. We take 4 balls, and if we take 2 bars, then we can separate the 4 balls into 3 groups, which correspond to the 3 boxes. Now notice I have N balls, 4 balls, and I have K boxes. And to make K boxes, I need K minus 1 bars. I can permute these symbols all over the place. How many symbols do I have in total? I have 4 of these ball symbols plus 3 minus 1 of these bar symbols, where 3 is the number of boxes. Okay, great. So in theory, I have actually N plus K minus 1 symbols here. How many ways can I permute all of these symbols? Well, N plus K minus 1 factorial permutations. Does it matter if I put this bar here or this bar here? No, it doesn't matter. So I have to divide out the useless bar permutations. That's K minus 1 factorial bar permutations. I don't need those. I don't need those. And the same thing here. If I move this ball here and this ball here, or this ball here and this ball here, it makes no difference to my problem, to the problem at hand. So I can divide out N factorial ball permutations. And here's an exercise for you. We're going to show, or you're going to show here, exercise 1, show that if I do that, I have N plus K minus 1 factorial, and I divide out N factorial for the redundant ball permutations, and K minus 1 factorial for redundant bar permutations, I end up with binomial coefficient N plus K minus 1, K minus 1. Prove this. It's not hard to prove, you could do that. So I have that. Putting N balls into K boxes, how many ways to do that? If the balls are indistinguishable, it's this many ways. Now, let's apply to staircase. I have staircase, and let's say each staircase is like a ball, and I want to put it into boxes. Let's say 1 box. If I put them all into 1 box, well, I put all 3 into 1 box. He takes, my climber takes 1 move, goes up 3 steps in 1 shot, okay? Assuming he's able to do that, okay? He can do 1, 2, 3, however many steps he wants to do, let's say. Okay, so this is 1 part. What if I want to have 2 parts? Well, I can put 1 in here, 2 in here. Here's 2 parts. 2 parts, and so on and so on and so on, okay? And the question is, what if I want K parts? I want K moves, or K parts. I want them to go up, let's say, an N step staircase, and he can go up, let's say, 2 here, 1 here, 3 here, and 1 here. So he goes up two steps, then 1 step, then 3 steps, and so on like that, okay? So by organizing the steps into boxes, I can then tell you what kind of motions he's making going up the stairs. So we want to know how many of these there are. Now, he cannot do 0 moves. So in fact, what we have to do is start with a position like this, where he does 1 step per box. Okay, so he has put 1 ball in each box because he's not able to do a 0 step. We do not allow that in our Fibonacci problem. I mean, otherwise the guy could just stay down here for 1,000,000 steps, right? Okay, so we don't do that. So in this case, we have k boxes and we have n steps. So how many balls did we use up? We used up n minus k balls. And now we can apply this formula for the rest of it, but with, we used up k balls. And so there's n minus k balls left. N minus k balls left. Okay, great. So our new n is n minus k. So let's use this formula here, and instead of n, we put n minus k. We have n minus k plus k minus 1, k minus 1, and we end up with this beautiful thing. Have a look. K's cancel out, n minus 1, k minus 1. So this is the number of ways to get up n steps in k parts, or k moves. Okay. So for example, let's take an example. We have 4 steps. 1, 2, 3, 4. We have 4 steps. We want to get up in k, let's say k is 2, let's say k is 3, and n is 4. So k moves, 3 moves. 1, 2, 3, for example. 1, 2, 3. See, I count this. I take 1 step here, 1 step here, 2 steps here. So that corresponds to 1, 1, 2, like that. Okay. How many ways to do this? All right. N minus 1, k minus 1. What is n? N is 4. 4 minus 1, 3 minus 1, that's 3, 2. What is 3, 2? 3, 2 in Pascal's triangle. 0, 1, 2, 3, 2 is 3. There's 3 ways to do it. Why don't you find all 3 ways? Okay, let's count all possible ways to do this for the case of n is 4. I have 4 steps. My climber can take 1, 2, 3, or 4 steps. So actually, here the number of steps he can take is actually exactly equal to the number of steps that there are. All right, let's start with 1 part. Okay, 1 part. How many ways to do that? Well, I have to put all of it in 1 box. He does it all in 1 shot. And let's calculate this. So 1 part. N is 4. N is 4. K is 1. Actually, I should do it here. N is 4. K is 1. Like that. 1 part. So n minus 1, k minus 1. What's that? 3. Well, I'll do it more carefully. 4 minus 1. 3 minus 1, that's 3, 2, and that's, actually no, it can't be. 1 part. Okay. 4 minus 1, 1 minus 1, and that's 4, that's 3, 0. 3, 0, and that's 1. And as you can see, there's only one way to do this. In 1 part, you got to take a jump of 4 steps. Okay, 2 parts. 2 parts. 2 parts. N is 4, K is 2. 2 parts. How many ways to do this? Well, let's count them. 1, 2, 3. That's 1 way. Here's another way. 1, 2, 1, 2. Here's another way. 1, 2, 3, 1. Is there any other ways? I can't think of any. 4 minus 1, k is 2. 2 minus 1, that's 3, 1. What's 3, 1? 3. We're right. This one right and this one right. Now, 3 parts. 3 parts. 1, 2, 3. Okay. 1, 2, 3, 4. That's one way to do it. 1, 2, 3, 4. That's another way to do it. That's another way to do it. I can't think of any other ways. Let's try this. 3 parts, n is 4, k is 3. Number of parts is 3. Okay, so let's calculate this. 4 minus 1, 3 minus 1, I get 3, 2, and 3, 2 is 3. And that's right, we got that. One more, 4 parts. 4 parts. 1, 2, 3, 4. As far as I know, as far as I can think through all of this, there's only one way to do it. There's 1, 2, 3, 4. There's only one way to do it. You distribute the steps this way, and he does 4 individual 1 steps like this. 1, 2, 3, 4. 1, 2, 3, 4. This way of going up the stairs corresponds to this distribution of balls in boxes. 4 parts, 4 minus 1, k is 4, n is 4. We got 4 minus 1, 4 minus 1, and that's 1. Binomial coefficient 1. Okay, how many in all? Let's look back. The whole thing added up. 1, 3, 3, 1. 1 plus 3 plus 3 plus 1 is 8. Okay, great. This is a good starting point, and in the next video we're going to continue this theoretical analysis, and we'll be able to solve the staircase counting problem in the most general manner imaginable. So if you like this, subscribe, because there's more coming.